For this question, we're looking at Chapter 15 data. Now with this in mind right here, we know the observation of a single car, 34.6, and the standard deviation. So we have the mean of 34.6, and we have the standard deviation of that with 3.6. What changes here from a Chapter 5 to a Chapter 15 problem is in this we are asking about the sampling distribution of the average of 150 cars. The sampling distribution of the average of 150 cars. So the mean of that sampling distribution for y would be just the mean we expect for a single car. Now think about this. If I tell you one guy is 5'11", what would you expect the average height of 150 guys to be? Well, one guy is 5'11", so I expect the average height of 150 guys, that's what that states, the average of 150 guys to be whatever the average of one guy is. So that's what we have right here. So in this in mind, once again, the mean of the sampling distribution of y bar is equal to the mean for a single observation, 34.6. That's what we expect. Going down further, the standard deviation changes right here, because think about this. If one guy is walking down the street and he's 6'3", is that weird? No, there's a lot of guys who are 6'3". But let's go ahead and visualize it with David M. Lane applet. If one guy is 6'3", which is, and let's put in the mean here, of 71 inches, and a standard deviation of 3. So one guy being 6'3" lands here at 75 inches, which is not so odd, but maybe a little bit odd. Now we need to take the standard deviation of 3 and divide it by the square root of 150. And what you're going to notice here is when we divide 3 by the square root of 150, it's going to get really tiny. Now what are we changing here? We're making the distribution tighter. If you notice, all of a sudden now, 75 is off the chart. And what this says is you are observing 150 guys with the average height of 75 inches, which is 6'3". Now that's really tall for the average height of 150 guys. That'd be a lot of really tall guys together. Or there could be some short ones, but the tall ones would have to outweigh them. So with this in mind, this is the distribution of the means. This is the distribution of the single observations. The distribution of the means is tighter because we are taking the standard deviation and dividing by the square root of n. So we have just shown the sampling distribution of the mean. Now the central limit theorem states that the larger n becomes, the more normally distributed this will become. And what we're showing here is an application of the central limit theorem. So with this in mind, let's go ahead and take a quick look at that. Let's punch in here. Central limit theorem applet. And let's go down to it. So let's say we have some crazy distribution. And I'm going to go here to custom. So with this crazy distribution right here, this is the parent population. What we are going to do is we are going to sample 150, and I can't put that many, 150 observations from this, and then take the average of those 150 observations to make a new point down here. We're taking 150 observations and then averaging them together. So pretend this was 150 different points taken from here and average it together. Now when you do this, if you notice, the new distribution is the distribution of the mean of 150 observations. And clicking this right here, if you notice, that looks pretty normal. But you say up here, wait, that didn't look normal. Well, what happens is you'll get some low, you'll get some high, but in the end it's all going to average out towards the center, which is here. This is the central limit theorem. The distribution will get tighter and normalize more. If I only put the sample size as 2, as in I'm just taking 2 points and averaging them together, well, that might not work. If you notice, it still looks like the parent population. At 5, taking 5 points and averaging them together, well, it's still not going to look so perfect. But you see it becomes more normal. At 20, even more normal. And 25, more normal. And watch once again that the distribution starting at 2 and going higher is getting tighter each time. This is because the standard deviation is being divided by the square root of n. And we can even test this in theory. When you take 5, let's go right here, 25, square root of 25 is 5, and then we're going to take the original standard deviation, divide that by the square root of 25, because that's our sample size down here, which is 5. 2.126, which is our new standard deviation down here of 2.13. So definitely we are seeing this in practice right here. So the distribution is approximately normal. Based on your answers to part 1 and 3, would it be unusual for the officials to see a speed of 37 miles per hour more? And we can get the z-score, and we can also visualize it. Let's go ahead. We see observation minus mean over standard deviation. Observation being the sample mean, mean being the mean of our data, and standard deviation being right there from obtained from the previous parts. So we can visualize this with the David-M Lane applet. Let's go back to it. Do I not have my, there it is. The David-M Lane applet. Let's put in our mean of 34.6, what we expected, our standard deviation of 0.2939, and I would draw this out on the test. I would always draw these, and now we see here the observation of 37, which goes way off here. That's very unusual. You wouldn't be able to get the area underneath here for above 37, and even here it's going to be very, very, very tiny. It's probably saying, it is saying 0. And the z-score once again is observation minus mean over standard deviation, and this is more than 3 standard deviations away. That is very, very, very odd. Good luck with this, and I would highly suggest drawing it out on the test, drawing this out right here, and even plotting 37 and saying, this is very, very odd. It is more than 3, more than 8 standard deviations away, and you could even solve for the z-score, which once again always is observation minus mean over standard deviation.